So in today's class, we are going to discuss about Fermat's and Wilson's theorem. It is basically the continuation of my previous class, where we have all discussed about modular arithmetic, and we have seen how easily by applying modular arithmetic, we can find out the remainder of any base whose exponent is higher. Though we have done that thing in binomial theorem, but yes, by using modular arithmetic, it can be solved easily. Now, while doing that class, I told you repeatedly that our prime task is to find out the remainder as 1 or minus 1. Why? Because the moment you get the remainder as 1 or minus 1, I can raise its power to any extent. The remainder will still remain either 1 or minus 1. That advantage we used to take. And all the mathematicians, they also worked on that. Fermat little theorem is one of that. Okay? So let's dive directly into our today's class. Fermat theorem states that if A and P are two co-prime numbers, that is HCF or GCD of A and P, that is 1. That is A and P are co-prime. Moreover, P is a prime. Then Fermat's theorem states that A to the power P minus 1 will be congruent to 1 modulo P. A fantastic theorem to bring 1 in the remainder directly. That is what I'm saying. Let us take an example like, let us say 8 and 17. Both are co-prime to each other. At the same time, 17 is a prime. So we can write 8 to the power 17 minus 1, and 1 is congruence modulo 17. That is, when 8 to the power 16 is divided by 17, the remainder is 1. Straight away we'll get that. That's the beauty of Fermat theorem. Is it clear? Is this theory clear to us? Okay, let me take one example. The question is, find the remainder when 2 to the power 50 is divided by 17. Now, we can all see that 17 is basically a prime. Moreover, 2 and 17, they are co-prime to each other. So to find out the remainder when 2 to the power 50 is divided by 17, we will start with 2 to the power 17 minus 1 is congruent to 1 modulo 17. That is 2 to the power 16 and 1 is congruence modulo 17. See? The remainder we are getting 1 directly by using Fermat's theorem. Now we have to reach to 2 to the power 50. So now I can raise its power to anything. So let me raise its power to 3. So again the remainder will be 1 again. So it is 2 to the power 48 is congruence modulo 17. But we have to reach 2 to the power 50. So what I will do, I will simply, 2 and 2, they are congruence modulo 17. So 2 square is basically 4, 2 square and 4. That is 4 is congruent to 4 modulo 17. That is when 4 is divided by 17, remainder is 4. So if I multiply the corresponding sides, we are going to have 2 to the power 50 is congruent to 4 congruence modulo 17. That is when 2 to the power 50 is divided by 17, the remainder is 4. See how quickly we are getting. It is actually, you see, your foundation is your modular arithmetic that we have done in the previous class. Those who have not seen the class, link has been given in the description. You can go there and check it. So Fermat theorem is basically, we are actually finding out the remainder 1 as quick as possible. So Fermat theorem helps us to do that. But here, 2 conditions are there. Number 1, P, that is the divisor, should be a prime, and the base of the dividend and the divisor, they are co-prime to each other. Only these 2 things we have to keep in our mind to get the remainder 1 very quickly. Okay? Let's take another problem. See this question. Find the remainder when 4 to the power 532 is divided by 11. Again, 11 is a prime, as well as 4 and 11, they are co-prime to each other. So I can directly write 4 to the power, from the Fermat's theorem, 4 to the power 11 minus 1 is congruent to 1 modulo 11. So 4 to the power 10, when divided by 11, the remainder is 1. Now I have to reach to 532. So all I will do is I will simply raise its power to 53. Remainder will still be there. That will be 1. So 4 to the power 530 is 1 modulo 11, right? But we have to reach to 4 to the power 532. So we know that 4 and 4 is congruence modulo 11. So 4 squared. So that is 16. Modulo 11. 16 cannot be the remainder when divided by 11. So it will be 5 modulo 11, right? So let me just multiply the corresponding sides. 5 modulo 11. That is, when this 4 to the power 532 is divided by 11, the remainder is 5. Is it not very simple? Absolutely. Okay. Let's take another problem. So this question, 7 to the power 222, when divided by 11, what is the remainder? Again, this is the prime number, and 7 and 11, they are co-prime. HCF of that is 1. So we can write 7 to the power 11 minus 1, and 1 is congruence modulo 11, right? That is 7 to the power 10 is, when divided by 11, the remainder is 1. Now we have to reach to 222. So what I will do is I will simply raise its power to 22. So that gives us, again, 1 modulo 11. That's the advantage we are taking. When the remainder is 1, that advantage we are taking every time, because we are raising its power. The remainder still remains 1 in that case, in all these cases. So it's basically 7 to the power 220 is 1 modulo 11. Now we all know that 7 and 7, they are congruence modulo 11. So 7 squared is basically 49 modulo 11. 49 cannot be the remainder, so let me just subtract 44 out of that. So it is again 5 modulo 11. And let me just multiply these 2 corresponding sides. We are going to have 7 to the power 222 is 5 into 1 modulo 11. That is, when 7 to the power 222 is divided by 11, the remainder is 5. Hence, answer in this case will be 5. Is it clear to everyone? Have you understood the Fermat's little theorem? The students, he will only understand who has already seen my modular arithmetic class, which is our previous day's class. Okay, now let's move for another theorem which is called Wilson's theorem. What does it say? Wilson actually worked on same thing, finding out the remainder. But he has worked on in factorials. Wilson's theorem states that if P is a prime, number, then P minus 1 factorial plus 1, which when divided by P, the remainder is 0. It means that if P is a prime, P minus 1 factorial plus 1 is completely divisible by P. That's the theorem. So we can modify this thing in this way. We can say that it means that when P minus 1 factorial is divided by P, the remainder is minus 1. It is the same way of saying. But the remainder cannot be minus. So from here we can say that P minus 1 factorial, when divided by P, the remainder is P minus 1. What I've done, I've simply added the divisor with the remainder. Now still in this, we are not very convinced, because what we are actually looking for, we are looking for in which way you can get the remainder as 1. I'm not interested that the remainder is P minus 1. That is what I want to say is, let us say P be 17. So Wilson's theorem states that if 17 minus 1, that is factorial 16, is divided by 17, the remainder will be 16. But again, I'm not interested in getting a remainder which is not 1, right? So now we will do a little modification in Wilson's theorem such that we get this remainder as 1. Okay? But before that, let me just tell you a very, very basic question. Suppose if I tell you what is the remainder when 35 is divided by 4? Pretty simple. You will simply say, sir, it is 8 fours are 32. Therefore, the remainder will be 3. When 35 is divided by 4, the remainder is 3. Okay, now let us try to do this in a different way. 35 means it's 7 into 5 divided by 4. Now this is same as finding out the remainder when 7 is divided by 4 into the remainder when 5 is divided by 4. When 7 is divided by 4, the remainder is 3. When 5 is divided by 4, the remainder is 1. Therefore, ultimately the remainder will be 3. So this way we can also think. And now let me just use this basic conception to find out the remainder, this one, as 1. Can we do that? Okay, let us try. Say this one. The remainder when P minus 1 factorial is divided by P is P minus 1. Clear? Now, P minus 1 can also be written as, P minus 1 factorial can also be written as P minus 1 factorial, P minus 1 into P minus 2 factorial divided by P, and the answer is coming to P minus 1. So from here we can write remainder when P minus 1 is divided by P into the remainder when P minus 2 factorial is divided by P, the answer should be P minus 1. Now when P minus 1 is divided by P, when P minus 1 is divided by P, what is the remainder? When P minus 1 is divided by P, the remainder is P minus 1. The remainder is P minus 1 when P minus 1 is divided by P into the remainder when p minus 2 factorial is divided by p, the answer is p minus 1. So we got the remainder p minus 1 directly from here. Right? Therefore, what should be the remainder of this such that the resultant remainder is p minus 1? Obviously, the remainder will be 1. Then only when you will multiply these remainders, you will get p minus 1 as a remainder. Are you getting the point? Therefore, a very important point we got that when p minus 2 factorial is divided by p, the remainder is 1, and that's exactly what I want. My purpose is solved because my purpose is to bring 1 as a remainder. That we got. And what is the modified form of Wilson's theorem? That is p minus 2 factorial when divided by p, the remainder is 1. Or you can say p minus 2 factorial is congruent to 1 modulo p, where p is a prime. Have you understood this? Is this much clear to everyone? Let's move for some problems. So this question. What we have learned, let me just write it here because this is the first time that we are doing, so it will be better if we write the formula over here. We have learned from the Wilson's theorem that when p minus 1 factorial is divided by p, the remainder is p minus 1. And the modified form of Wilson's theorem is that when p minus 2 factorial is divided by p, the remainder will be 1. These two things we got. Now, let us check the first question. The question is 41 factorial when divided by 43. 43 is a prime number. So we all know that p minus 2 factorial when divided by p, the remainder is 1. So your 43 minus 2 factorial when divided by 43, the remainder will be 1 only. So what we got? We got 41 factorial when divided by 43. The remainder is 1, hence the answer for this is 1. Now see the second question. When factorial 8 is divided by 11, we all know that from the Wilson's theorem that 11 minus 1 factorial when divided by 11, the remainder is 11 minus 1. Am I correct? That is, factorial 10 when divided by 11, the remainder will be 10. Okay, so what we got? We got that when factorial 10 is divided by 11, the remainder will be 10. Now, this can also be written as 10 into 9 into factorial 8 divided by 11. The result is, the remainder is 10, which is same as finding out the remainder when 10 is divided by 11 into finding out the remainder when 9 is divided by 11 into finding out the remainder when factorial 8 is divided by 11. But the answer will be 10. When 10 is divided by 11, the remainder is 10, which can also be written as minus 1. The remainder will be minus 1. When 9 is divided by 11, the remainder is 9, but we can write this thing as the remainder is minus 2. And this remainder we actually need. So let me write it as R, which is equals to 10. Therefore, we are getting 2 into R is basically 10. Therefore, this R has to be equals to 5 to get the final remainder as 10. Therefore, the remainder when factorial 8 is divided by 11, it is nothing but 5. Is it clear or not? And that will be your answer. Isn't it very easy to solve this kind of problem when factorial is involved in it? Whenever factorial is involved and we have to find out the remainder, we will always think about Wilson's theorem. Let me take another example. See this question, find the remainder when factorial 21 is divided by 361. So we have to actually find out the remainder when factorial 21 is divided by 361. But unfortunately, here we cannot use Wilson's theorem. Can you tell me why? Because 361 is not a prime number. And that's the reason we cannot apply Wilson's theorem. So what to do? Okay, let me write in this way. This can be written as 21 into 20 into 19 into factorial 18 divided by 361 can be written as 19 into 19. Right? So let me do one thing first. Let me just cancel the common term that we are having, which is your 19 and 19. Okay? So we are basically getting what? We are getting what is the remainder when this 21 is divided by 19? What is the remainder when this 20 is divided by 19? And what is the remainder when factorial 18 is divided by 19, right? Now, we can easily see that when 21 is divided by 19, the remainder is 2. When 20 is divided by 19, the remainder is 1. And when factorial 18 is divided by 19, the remainder is 18. Can you tell me why? Because from the Wilson's theorem, the remainder when p minus 1 factorial is divided by p, the remainder is always p minus 1. Okay, p is a prime number. Here 19 is a prime. So we are getting the answer as, the remainder as 36. Now there is a major mistake what students used to do. They used to give the answer that, yes, when factorial 21 is divided by 361, the remainder will be 36. Absolutely wrong. I'm telling you why. Because have you observed one thing? You have already cancelled one term. So the remainder will be not the term that we got. It has to be multiplied with 19 to get the final answer. Let me write it here so that you will understand it clearly. So your final answer will be not 36, but it will be 36 into 19. Can you tell me why it is so? Because, look it carefully, because let us say if AT is divided by BT, if it is divided by, let us say BT, and say we are getting a remainder, K. So what you will write? You will write AT is BT into some quotient, let us write the quotient as Q, plus the remainder K. Now from the dividend and from the divisor, if we cancel T, that is what I want to say, I am dividing both the sides by T. So you are actually getting K over T. So when you want to find out the actual remainder K, what do you have to do? Whatever answer I got, that is the remainder when A is divided by B. The remainder has to be multiplied with T to get the actual remainder. Are you clear or not? So here what we have done, here the divisor was 361 and the dividend was factorial 21. So from the dividend and the divisor we have cancelled 19. So to get the actual remainder, you have to multiply that cancelled term. In this case, it is 19. Is it clear? Therefore, our remainder will be, it will be 684. But 684 cannot be the remainder when it is divided by 361. So let me just subtract 361 from here to get the actual remainder as 684 minus 361. That gives us 3, 2, and 3. So 323 will be the remainder when factorial 21 is divided by 361. Is it clear to everyone or not? Have you understood this conception? Very, very wonderful method of finding out the remainder when factorial is involved in the question. Okay, so let me take this sum. Find the remainder when 39 factorial is divided by 41. This sum I'm giving you as your homework. Do this sum, write the answer in the comment section. Okay? So see you tomorrow. Till then, take a very good care of yourself.